So last time we discussed an algorithm which I have up on the first board here. So as always, let K be a field, consider this multivariate polynomial ring and with a fixed monomial ordering. And last time we proved that there was an algorithm which, given some element of the polynomial ring and a non-constant or a sequence of non-constant polynomials, which computes an expression of the following form, basically a sum of powers of this sequence here with coefficients which are not divisible by such that their terms are not divisible by any of the leading terms of the TI. In this talk, we're going to go on to discuss a way we can use this algorithm to define a sort of generalized differentiation with respect to such sequences, which satisfy a couple more conditions. So let's make a start on that. Okay, so what we're going to do is we're also going to consider the polynomial ring kxy, where this thing is basically just the same polynomial ring we had before with, xm, with another copy of the variables, which we're now calling y, right? And we're going to define another sequence, ti, which is a polynomial in the polynomial ring kxy, which is the difference of the t of the little ti evaluated on each of the different variables, like so. And we're going to call the sequence of these big T's like so. Okay. And now what we need to do is we need to extend the monomial order to on kx to a compatible monomial ordering on kxy, right? And basically, the idea of this is to extend it lexicographically on each kind of part of on each part of these variables. So I'll be precise about that. So extend the monomial order, say, let's call it greater than with a subscript x on kx to kxy, like so. So we say that a comma b, where this thing lives in nm cross nm, is greater than a prime comma b prime if and only if a is greater than a prime with respect to the original monomial ordering, or if a equals a prime and b is greater than b prime. Okay, it's fairly easy to check that this does indeed define a monomial ordering, and it has the property that when we restrict it to polynomials involving only x variables, it agrees with our original monomial ordering, and it's a monomial ordering in which variables or terms rather involving x dominate terms involving y, right? So in particular, we have that the leading term of, say, a polynomial in only x variables in our base ring, right, in our original polynomial ring, is the same thing as the leading term of the sum of these two polynomials, like so, in the ring kxy, right? From now on, I'm not going to bother distinguishing between these two different monomial orderings, and I'm just going to use like the usual leading term notation to refer to both. Okay, The next thing we need to do is so let's take a look at the board number 3. The next thing we need to do is to consider some conditions on our on the sequence T under which we can go on and make this definition, which I'm getting to. Okay, so we're going to suppose two things. First of all, that T is what is called quasi-regular, and that T is a Grosvenor basis. By that I mean it's a Grosvenor basis for the ideal that its elements generate. Given this, well, this condition implies that T is also quasi-regular. No, I haven't defined quasi-regular yet. And I think it's possible that this implies that T is also a Grosvenor basis. But I haven't checked yet. And if that's not the case, then we also need to assume that big T is a Grosvenor basis as well. Okay, I'm not going to define quasi-regular or actually Grosvenor basis. I haven't defined that in this series of talks either. And the reason we're making these assumptions on T, on little t and big T, is so that they have the following property, that they satisfy the following lemma, which I'm about to write down. If you're interested in these properties and why they mean that the following lemma is true, there's an appendix in the notes, but I don't really want to get into it now. Okay, so the key takeaway from these conditions is that the following fact is true. So if f is in kxy, or sorry, in kx, then any expression for f of the form, oops, now say f is like this. So where RU is not equal to 0. What am I trying to say here? Where finitely many RU are 0, and all terms of the RU are not divisible by any of the leading terms of the TI. So this is a statement about expressions of this form. So if any expression of this form is unique, right? By that I mean the coefficients in this expression are uniquely determined by f. Okay, and likewise for such expressions of polynomials in the ring kxy, right, where we're replacing, so I guess I should say replacing t with little t with big T, right? So that's the key takeaway from these conditions. Notice that this expression is exactly the same type of expression that is computed by the algorithm that we defined last time, right? So together with the results from our last talk and this result here, we know that every polynomial in both the ring Kx and the ring Kxy has such an expression, and this lemma tells us that those expressions are unique. Okay. Okay, we're now ready to actually go ahead. I guess actually there's a couple more bits of notation I want to define. Do I actually need that quite yet? Let me double check. Okay, no, I'll come to that a little bit later. So now we're actually ready to start defining these maps, which are gonna act like division. Okay, so we're gonna fix some f in our base polynomial ring, which is where we're wanting to define this differentiation, and we're going to write the polynomial f of x minus f of y in its unique expansion in terms of the big T variables, right? Okay. And for each, so U in this indexing set, define a map from, so we're going to call it rho. So this is not our final differentiation map, but something we need along the way from kx to kxy, which is given by setting rho u of f to RU of f, right? So it's just the map that gets the coefficient of, the coefficient indexed by u in this expression for f of x minus f of y. Okay, right. So now we're going to start proving some properties of these maps, and we're going to get to the point where we can define this differentiation thing. Okay, so first of all, we need to show that this thing is linear, right? K-linear. So let's do so. So rho u is K-linear. Okay, proof. So I'll take f and g in kxy, sorry, in kx, I guess c and d in the field k. Then we have that cf plus, dg of x minus cf plus dg of y. Well, that's the same thing as, whoops, not quite, c rho u of f plus d rho u of g. Right. Okay, and notice that no term of c rho u of f plus d rho u of g is divisible by any of the leading terms of the Ti. Notice, by the way, I should have mentioned this before, that these leading terms are the same as these leading terms. Okay, so notice that that is the case by uniqueness, by which I mean the lemma that I wrote up on the previous board. We have linearity. So in other words, we have that rho of rho u of c f plus dg is equal to c rho u of f plus d rho u of g. Okay, that's good. Okay, now let's take a look. We'll go back to the first board again. The orb come along. There we go. Okay, so now I just need to define a little bit more notation, sort of extending the ideas of factorials and binomial coefficients to n to the n. So for u and v in n to the n, define u factorial, or u exclamation mark, I guess, as just the product of the factorial of each of its entries. UN factorial, right? And then we also define this sort of binomial coefficient type thing. V choose U, I guess, is how I would say it, like so. So it's going to be 0 if any Vi minus Ui is less than 0. So if any entry in that difference is less than 0, and otherwise it's just going to be sort of the usual form we're used to. That should be a V on top. Okay. The next thing to prove is that this thing sort of works nicely. So this map row, or rather the maps row U, work nicely on the powers of the sequence T, right? So lemma. So row U of, say, T to the V, that is going to be V choose U of T to the V minus U of Y. Okay? So for all, this is going to be true for all V not equal to 0. Okay, proof. So I claim that it suffices to show that TV of X, that this thing, we're thinking about this now as an element of the polynomial ring XY, that this thing expands like so. Okay, so why is that the case? So having shown this, which we'll do momentarily, we have that TV of X minus TV of Y, that thing is equal to, well, it's just rewriting this sum, right? So for all U not 0, that is this thing, oops, V U okay, okay, looking here, no term is divisible by the leading term of Ti, which is the same thing as the leading term of Ti. The reason for that being that these leading terms are exclusively in X, and this is a polynomial exclusively in Y. Okay. So we're going to prove, I guess, so I'll give this expression a number. So we're going to prove 1 by induction. And we're going to induct on the sort of, I guess, degree of V, right, which is going to be the sum of its entries. Okay, so if V is 0, then 1 is true. Both sides are equal to 1. Oh, sorry, I think I stated this slightly wrong. In the statement of the lemma, I said for all V not equal to 0, this should have been for all U not equal to 0, right? So the U being the index of the map, not the power of t. Sorry about that. Okay, so where were we? So if v is 0, then it's fine. Suppose v is strictly greater than or equal to 1. Let I be such that vi is greater than 0. Okay, and then we use the induction hypothesis. So we have t v of x. Well, that is the same as ti x of tv minus ei of x. Okay. That makes sense because vi is not 0. That is the same thing as ti of x. Like so, using the induction hypothesis. Okay. Then we can rewrite this sort of coefficient sitting out the front here. We can rewrite this as ti of y plus big Ti, right? So that's just remembering what big Ti is defined as. Okay, and then what we want to do is we just, I guess, expand this out. Let's see. What am I doing in these two steps? Okay, so the first one becomes this thing. Okay, there's a little typo in this proof in the notes. What I'm doing here is I'm re-indexing this thing in the second sum, offsetting everything by a factor or by a movement of ei. Okay. And then this from now on, at this point, we can write this down as. I guess I'll show the steps, right? So we get TV of y plus all the terms where u is not 0, and this is going to be okay. And this thing here is an identity of binomial coefficients, and it works for this sort of this extended version of binomial coefficients that we have as well. And it's, I guess I'll just continue on the next board. I'll go to board 4 because I want to keep that lemma up. So working from the previous board, that's going to become TV. So applying this identity, I can't remember what it's called. So VU, this thing comes out as TV minus U of Y to U, which is, of course, exactly what we wanted to get. Okay, so we're sort of in good shape, right? This thing is starting to look, well, it's not quite what we want because it maps to the polynomial ring KXY, but it's starting to look a lot like what we want, right? It's sort of working nicely with the powers of the TI, it's K-linear, and the last thing we need to prove about it is that it sort of, is that it works nicely with the things we want to act like constants, right? So that's what this next lemma is about. So for F in, so KT, right? So this thing is the K algebra generated by 1 T1 Tn in Kx. So for F in KT and any R in Kx, right? Such that no term of R is divisible by any of the leading terms of the TIs, same condition as always. And for any, so we have the following fact for any u not 0, that rho u of R times F is the same thing as R of X times rho u of F, right? I'm specifying the variable here because now this thing lives in KXY, right? Okay, proof. Suffices to show for F equals TV. The reason for this is these maps we already know to be T-linear, and this thing is, sorry, K-linear, and this thing is, just sums of T's with K's with elements of K in front of them. Okay, so let's figure this out. So we'll compute this, I guess, like so. So TV of X minus RY TV of Y. So let's add in an extra term.
Why exactly are you writing R of X?
Because I'm specifying that it's R evaluated at X, and now it lives in the polynomial ring KXY. So it's different from the polynomial R of Y.
You wrote R as in Kx to start with. Why would I think it involved Y's?
I guess, so R lives in Kx, but we could think about it as evaluating, so we can think about it like evaluated at X, or we can think about it evaluated at Y, at the variables Y.
Okay, so
right?
It's just because in the proof
KXY.
You're also writing RY, you thought it would help to spell out explicitly that it hasn't secretly changed to being R of Y from the last sentence.
Yeah,
okay.
I guess so, because I suppose what I'm thinking is let R be in these two polynomial rings, which are really the same.
Okay.
is what's sort of in my background.
I feel like by anticipating my confusion, you are inviting me to make the confusion. But yeah, fine. Okay.
I mean, it's the same reason I'm writing TV of X here, right, to distinguish it from the TV of Y.
Yeah, there I guess I see the purpose. All right. Anyway.
And it felt sort of inconsistent to not do so for this polynomial. Okay. Okay, so I'm just adding in this extra term and then subtracting it. And then we'll keep the old thing on the end. Okay, give ourselves a bit more space so we can factor this thing. Okay. Next, we want to use what we just proved, right? So we want to have R of X. Now this thing becomes this sum. And this thing stays the same. Okay. What have I done in the last line? I've just moved this thing inside and sort of reorganized it. And this should be not equal to 0. Oops. Yep, where am I up to? V minus u of y du. Okay, and I guess now we go through and we notice that no term by any of the leading terms of the TI. That's because, well, that's true of, certainly true of this part, and then this thing is just a polynomial involving the y variables, so it can't create a term when multiplying here, which is divisible by something something involving only x. And it's a similar story here. It's not divisible by this thing, and then this thing involves, well, that's not clear, but this thing involves only y variables, right? Oops. Okay, I guess let's go take a look. I'll just go straight back to this board. Okay, so what can we conclude from this? I guess we can just conclude from here, right? Because we can take a look at the coefficients here, and that's the coefficients that we're trying to prove this for. Okay, great. So now we're going to define the maps that are going to become our system of derivatives. Okay, so let phi from kx y to kx be the morphism identifying xi with yi. Okay, and for each ti, define the following map. By setting, so we'll set ti of f, that thing is going to be equal to phi of rho of ei, right? So the coefficient of Ti in this, or of big Ti in this expansion sort of thing we've been going through. Okay, and essentially what we've already shown proves that these T1 through Tn, so T del Tn, form a system of T derivatives. Right. So for that, I guess this isn't really much of a proof. We've pretty much already proved it. So for that, we need k-linearity. That is clear, right? We've shown that. We need this every f in kxy, or so in kx, is of the form tu, with ru in the kernel of all of these things. That's certainly true, right? We have this unique expression stuff that I went through at the start, the algorithm giving the expression and the quasi-regularity and the fact that T is a Grobner basis giving the uniqueness. And what else? And all these coefficients which don't divide, in which none of the Ti terms are divisible by any of the leading terms of the Ti, that they all sit in the kernel, clearly, of del Ti. Okay, the next two are pretty clear, right? We know that del Ti of TV is Vi times del TV minus Ei, right? We proved that. We did that as a special case. So this is a special case of the same sort of looking lemma we did with the rows, just looking at row of Ei, and then identifying x and y in that expression. And then finally, we wanted to show for f in kt, hopefully I can squeeze this in, and in this kernel, that we have del Ti of Rf is R of del Ti of F, and that's pretty much exactly what we just showed, right? If we identify x and y in that expression. Okay, so that's sort of what we were claiming to do. What I was claiming we could do, proved in the special case for a Grobner basis. So for when T is both quasi-regular and a Grobner basis. It doesn't cover all of the cases that we need it to in order to set this. So, thinking back to this big picture of what we're doing, right? We wanted to come up with this strong deformation retract between this causal complex and the Jacobi ring. In order to do that, we had to come up with this system of T derivatives, but we wanted that strong deformation retract to start talking about the cut operation on in the bicategory of Landau-Ginzburg models, right? So assuming that T is a Grobner basis means that we can't use these maps for all of the possible potentials in the bicategory of Landau-Ginzburg models. So there's going to be potentials whose partial derivatives don't form Grobner bases. Now, what I've recently figured out is that in the case that this does not form a Grobner basis, so actually this Grobner basis condition can be weakened very slightly, but really in general, when these things don't form a Grobner basis, you need to pass to the formal completion of the ring Kx with respect to the ideal that the TIs generate. I don't think we're really going to get to that in a talk, at least, not anytime in the next couple of weeks. but that'll be sort of upcoming in my thesis once that's done. I suppose now's a good time for questions. And after that, if we've still got a little bit of time, there's some other sort of facts we can prove about these. There's one more fact I want to maybe prove about these maps that's sort of not really needed, but it's sort of interesting. But yeah, if there's any questions now, it's a good time to talk about it.
So what was the status of the T minus T being a Grosvenor basis? We still don't know that, but that's being used, right?
Yeah, that's true. So have I erased this? Yes, I have. Yeah, so I haven't looked at that. I don't know whether that's true or not. It's certainly true for many examples you can come up with. But yeah, I guess short answer is yes, it is not known. So yeah, that would also need to be included as an additional assumption if you're wanting to use this approach.
I don't want to put words in your mouth, but I guess would you agree that what you've presented here is kind of the situation where everything is quite elegant and straightforward, and then, well, maybe the T's aren't always a Grosvenor basis, but you can do things like this, just more complicated things in the general case, but it doesn't hurt to see this first also.
Yeah, I definitely agree with this. It's a similar story in the general case, but exactly as you say, more complicated. And I think it's also an interesting case because at least using the approach that we've been talking about, it's the only case where you can actually explicitly compute every single one of these maps exactly, right? It seems like, or at least that I know of, maybe there's another way. In the general case, you can produce approximations in the completion, but I guess that's not quite the same thing as actually computing them pointwise. So I guess this is maybe a useful place to look for examples of cuts and things like that.
Cool.
If there's no other questions, I'll get on and talk about this last sort of result. So I guess this is sort of tying, if you remember back to the previous talk I gave right at the start, I was going on about how we can prove a sort of version of Taylor's theorem for sort of in an algebraic setting. And this is sort of what this whole approach is inspired by, right? And this next lemma is basically the version of Taylor's theorem that holds for these maps. Okay.
You might need to move forward a bit.
So
the orb didn't quite follow you.
Sure.
There we go.
Is it coming now?
Yep.
Cool. Okay. So, whoops. So we don't actually use this anywhere, but it's sort of interesting, or at least I think so. So we're going to define the map TA del sub T superscript A. So this is just going to be the composition of these maps. Where A lives into the N, right? And this thing just means apply T1 A1 times. So noting these maps commute. I guess to see those maps commute, you can compute the lemma that shows the lemma that's written up on the previous slide that shows it's a I think we proved that maybe for a general system of T derivatives. Anyway, you can show it using the lemma we just showed, not too difficultly. Okay. Point is that there's no ambiguity, there's no sort of choice being made about which maps to apply first. Okay, so I guess lemma. We have that del superscript A sub T, that is a factorial times rho of, phi, so that being the map that identifies X and Y, rho A, right? and this is true for all a not 0. Okay, so proof. Okay, so we're going to let f be in there, and write f of x as this thing. Right, as we've been doing. So here, these coefficients, I don't want to write it all out again. These coefficients, finitely many of them are non-zero, and no term of these things are divisible at any of the leading terms of the TI. Okay, now we have that rho sub A of TUV, TU, T to the U, that thing is this. Whoops, sorry, A here is a U. And so, right, we have that this thing here. So that doesn't follow from what I had above. That follows from, I guess, just applying the maps. And we can write that as like so. So this follows from what I had above. Okay. That becomes that thing, and we can take this coefficient r inside of the phi, right? Because it's a polynomial involving x. Yep, and it also commutes past this thing because of a lemma we proved. Sorry, I guess moves past this thing because of a lemma we proved. So we end up with not quite this, but with rho a ru tu. Okay, and then applying linearity gives us a factorial phi rho a of f. Okay. And that completes the proof of this lemma. I guess we're sort of out of time. In the notes, if you're interested, I've got an algorithm. It's more or less obvious, right? But you can compute these maps, these del TI maps, using exactly two applications of the division algorithm. So in order to compute this system of partial derivatives, you don't need to apply the division algorithm in order to fully expand everything. You can just apply it twice in the polynomial ring kxy to get the coefficient that you're after. So I guess that's another byproduct of this approach. But yeah, that's about all I have to say. There's some more stuff in the notes on the quasi-regular sequences and Grosvenor basis stuff. But yeah.
Thanks, Rohan.
That's about it. No worries.
So, yeah, what would you plan to cover in 2 weeks? If that's clear.
Yeah, I think the next thing to go on to is like going back to the cut operation, actually like doing that. So I sent Will a message today because at one point he indicated he was sort of interested in starting to talk about this. So I'll sort of chat with him, and if he wants to present that, then that is good for me. If he doesn't, then that's fine by me as well, and I'll just present that.
Cool. Sounds good.
Cool.
All right. Thanks. I'm off to AI safety.